It's a pleasure to be here. As Brian said, my name is Mark Bourke. I cut my teeth sort of like neutron scattering at a couple of research reactors in the United Kingdom called Dido and Pluto, which don't exist anymore, and did a lot of my thesis working at ISIS and at the ILL in France. And then in about 1990, I came to Los Alamos. My undergrad degree was in physics, and my PhD was in mechanical engineering. I'm going to guess that we've got the usual mixture of physicists and chemists and biologists. I wondered whether there's anyone in this room that sort of self-identifies as an engineer. Okay, great. And like electrical, mechanical materials. Great. Okay. So I guess I'm pitching my talk to you a little bit, but I'm also pitching my talk to those of you in the room that maybe don't want to be professional full-time neutron scatterers or X-ray physicists, but see the opportunity in interpreting sort of some of the fantastic techniques in sort of neutrons and X-rays that you've learnt about, and communicating what the impact is to a different audience. And there's opportunity there. One of the reasons that interpretation is important is that although it might be slightly hard for you to notice, the return on investment as measured by the Office of Science, right, for giving you beam time on instruments here is typically sort of science productivity. So the scientist and the productivity of the facility is measured based on how many papers, how many phys revs, how many active mats you get. And that means that for the sorts of problems that I'm going to be talking to you about, there's a little bit of tension sometimes, right? Because what engineers want out of the measurements, taking advantage of the unique insight, doesn't always lead to publications. And so there's a real opportunity for those of you that can straddle the gap between the science, right, and the practical applications to actually provide capability while simultaneously satisfying the return on investment that the Office of Science needs. And I hope that comes out a little bit as I talk. So I want to just introduce the theme by talking about, what motivates engineers. These pretty pictures, and I imagine by this stage you're relatively saturated. So I have two equations, and probably they're variations of equations that you've seen before, so you can be fairly relaxed, I hope. These are just pictures that relate to problems that have come across my desk, whether it's working at the neutron source in Los Alamos or APS or some of the other facilities. Top right, you will recognize a reactor. One of the challenges that engineers have, just by way of example, is to come up with better cladding for nuclear fuel. Right? So one of the reasons that Fukushima was as bad as it was a function of the cladding that used. Right? People in the reactor industry tend to be very conservative, don't change out materials, and so you say, well, are there better cladding materials you can use? And now, what can you learn? What can you tell me about them? It's an engineering problem. Another problem that has come across my desk relates to materials that goes into satellites. There's a perennial need for light and strong that has, reasonable reliability in the face of thermal cycling and the radiation damage you get in space. Can you tell me a new material? I don't necessarily need to know everything about it, but I do need to know what it is, and I need to be able to certify it and say that it's safe to put up there. And then, of course, there's lots of sort of corrosion issues. Another motivation for engineers relates to economic impact. Those of you that, I think by now you've been exposed to, the residual stress problems, sort of like here, and I'll be talking more about them. May not be aware, but pretty much, I think every fan blade in a Rolls-Royce engine has been laser shock peened. It's a treatment that you use to impede fatigue crack growth. You better believe that for a business that's $60 billion plus or minus, that people are interested just in whether or not those residual stresses have been put in reliably and uniformly, right? It's not science, right, per se, because it's an engineering question. On the other hand, the tools that you've been learning about, whether they're neutrons and X-rays, can certainly address that question. And of course, a fundamental question for engineers, is it safe, right? This is a binary question. It's a question that the answer is yes or no, right? And so, whereas we can vacillate a lot in the science and say, well, maybe, in the question of safety, it either is or it isn't. And so there's this perennial tension between product quality and process cost, right? Now, let's just sort of broad lead into the discussion, but if you picture those sorts of questions and then map them to the insights that you've been getting, whether it's in diffraction or reflectivity or inelastic, you can start to see, well, with the knowledge that I have, can I translate those insights to a community that doesn't care about the science but very much value the insight that you can get? So what I'm going to do for you is basically talk to you a little bit about Los Alamos, explain the engineering context of what we do, talk about Lance a few moments, then hopefully add a little bit of value by giving you some historical perspective of the sort of stress measurement technique for those of you that are mechanical engineers, and those of you that are interested in sort of how you ended up with the measurements that you're doing on HIFA, on I think friction stir weld, or the sorts of activities that are going on Vulcan. I'll talk about instrumentation, then I'll talk about basically two examples. One relates to a uniquely Neutron measurement, which relates to bridge cables, and then the second relates to a series of relatively new activities that we've been doing at the APS. And the reason I chose those two was sort of both to identify the opportunities with neutrons and to show to some extent the complementary aspects of them. Oh, by the way, I'm quite happy for you to jump in with questions if you want to sort of interrupt as I'm going along. It makes it more interesting for everyone. So, Los Alamos. There are, you've been at Oak Ridge, you went to Argonne, there are two national labs. They're both part of the Office of Science, BES-funded labs. There's another class of labs that are funded by the NNSA, the National Nuclear Security Agency. Los Alamos, Livermore, and Sandia are the primary ones. The Los Alamos budget is about $2 billion a year. It's got about 10,000 employees. About half of those employees work outside the fence on a range of sort of scientific endeavors, primarily focused and underpinned by national security issues. So it's everything from cybersecurity to, infrastructure, roads, biological, but you can map, national security, lots of things. But the key activity at Los Alamos, and the reason it's there and the reason it's been there since 1943 plus or minus, relates to the nuclear weapons program. And the key mandate for Los Alamos right now is how do you establish and satisfy yourself that weapons that are in the stockpile are safe, reliable, and secure. At one level, that probably seems like a relatively benign question, but at a different level, if you think that, you need to be confident that something that has been sitting in the stockpile for 20 or 30 or 40 years, right, is going to operate just the way you want it to. And this is a very complicated system. It's a system that's undergoing radiation damage, it's undergoing thermal cycling, it's undergoing some corrosion. And so, without going into the details, you can actually dig into that and find that there's a lot of engineering questions relating to corrosion, relating to thermal cycling, relating to cracking, relating to fatigue cracks that exists in these rather sort of complicated, important objects. And so for that reason, Los Alamos supports, right, actually, yeah, and so this was just making my previous point. So some of the, the engineering challenges that we engage in relate to, if you're going to replace a material using an additively manufactured component, right, what are the questions you need to ask in order to be confident that a component that, may have very different microstructure behaves the same way in an extreme environment? If the goal is to replace high explosive in a bomb or a warhead with what's called an insensitive high explosive, which is safer. It's safer for a variety of reasons. How can you be confident that the performance is the same? And then there are lots of questions that relate to sort of like fundamental physics of mechanical performance under extreme conditions, right? It's not really a talk about the sorts of dynamic issues that Los Alamos cares about, but you want to be confident that a metal that performed and deformed in one way, 20 years ago performs in the same way, sort of like in 2020. So by virtue of that fact, Los Alamos supports a variety of facilities. There's probably a dozen or so, sort of like ranging in scope, to actually probe material science, probe those sorts of questions in different ways. The one that's pertinent to us here today is the Los Alamos Neutron Science Center. Right? So before there was SNS, there was IPNS, and after IPNS, there was the Lujan Center. The Lujan Center hangs off a linear accelerator. It's a proton accelerator, 800 MeV, about a megawatt in power. There are basically 5 facilities that run off this facility, which, qualitatively from 30,000 feet looks similar to SNS. It's very different in practice. There's the Lujan Center, which has got a variety of instruments not dissimilar to the ones that are here. Power of the source is probably, 10, 20, 25%, depending on your metric that you want to use. But you can do the same sorts of things that you do here, primarily focused on sort of diffraction and engineering physics right now. There's a facility for doing nuclear physics, which is a fast neutron unmoderated target. There's a lot of isotope works goes on there. There's a UCN facility. There's an isotope production facility, and then there's also a proton radiography capability where we do a lot of dynamic radiography, sort of studying shock and materials response, sort of like at the microsecond to nanosecond timescale, primarily relating to sort of trying to capture sort of like detonation. So now with that as preamble, let me turn to a brief historic perspective of stress measurements. So I think that you're doing measurements at Haifa. Good, all right, so a few nods, that helps. So the, and again, for context, I started making measurements sort of like at the Dido and Pluto reactors, sort of like using very similar approaches, the sorts of things you're doing at Haifa. Sort of graduated sort of through and eventually built one of the engineering spectrometers at Los Alamos called SMARTS, which is a variation on Vulcan. To put it in context, and I think this is just to let you sort of see the background of how you've ended up here, right? And I'm gratified to see that 10% of the people were from engineers, sort of like the opportunity, sort of like for actually using these for engineering. But to put it in context, residual stresses, residual strains were first alluded to in about the 20s by Hein, who suggested that there was some kind of elastic strain present after plastic deformation. In the late 40s, Greenough actually defined the term residual strains in plastically deformed metals, right? And then pretty quickly after that, this parlance of type 1 macrostresses, type 2 microstresses, and type 3 microstrains came into being. The the fact that neutrons could potentially touch the problem was first recognized in the 70s, where Hank Prask, who was at, I'm not sure where he was at then, but he did most of his work at NIST, working with these guys from the Navy, basically made this observation: neutron technique may be sufficiently sensitive to strain as induced by residual stress to have practical utility, right? Neutron depth profiling might be useful for measuring subsurface residual stresses. Right? It's an observation that, because you can probe, because objects are sort of like metal, and you can still get an appreciable neutron signal through an inch or so of steel, right? You can make measurements, right? And they made this observation: depth profiling might be useful. The first actual measurements of neutron depth profiling with residual stress happened in the 80s. Those of you that have spent any time at NIST might possibly recognize a very youthful looking Andrew Allen, who sort of like works there on their small angle scattering program. This activity, which actually led to a paper in this NDT, which is a non-destructive testing journal, led very quickly to the first commercial work, right? As they actually, people saw what they could do, and then the Dunray fast reactor said, well, okay, can you make some measurements of residual stress in a well for us? And they took the first chunk of money for actually doing these measurements at the Harwell reactor. In passing, I would note that in the community, there's a little bit of tension as to who sort of did this first, because this set of people, actually, they're not around these days, right? Wanted sort of some credit for doing it first, but actually, the first people that got journal publications were this set, right? And so in the community, there's been a little bit of tension of occasions looking about that, but it's ancient history now. Over the course of the 80s and then into the 90s, the engineering community, the mechanical engineering community, the people that cared about these sorts of problems, said, wow, neutrons are fantastic, how are we going to do this? Of course, in the 90s, the third gen synchrotron X-ray sources came along, right? And whereas, in 1990, if you'd asked me, how am I going to do a residual stress measurement in a piece of steel that's this thick, I'd say the only game in town is neutrons. Right now, right, with the onset of high energy photons between 50 and 150 keV, that you can tune, you can actually push through appreciable thicknesses of materials, certainly, low-Z materials like aluminum, but even things that we care about, uranium, right, you can actually get through pretty big chunks of material. Now, as you'll see, right, the nature of the measurement is a little bit different, right? And it turns out that there's plenty of space and complementarity between the two techniques, but it's important to look at both of them at the same time. Another important note to pay attention to is that if you're going to engage an engineer, right, in the measurements that you want to the unique measurements you're going to do, one of the things they typically care about is the standards, right? They want to be confident that a measurement that you make at SNS is the same as a measurement that you make at ESS, is the same as the measurement that you make at Los Alamos, if they're going to use those results to sort of draw a conclusion other than something that you can put into a peer-reviewable paper. Peer-reviewable paper, you can have all sorts of caveats, right? You can say, look, this is the measurements. You can be completely legitimate and say you've got some errors. If an engineer is going to draw a conclusion about whether a bridge is safe or not based on the measurement that you've taken, you've got to have standards. And so over the course of the 90s, there was a lot of work, particularly in the neutron community, to establish and define standards for making measurements. That meant that there was a series of activities making what were called round-robin samples. Right, this was an example of one of them. It was a very simple, sort of rather elegant sort of thing. It was just a piece of an aluminum cylinder with a mismatched plug. So you take the aluminum cylinder, you put a hole down the middle of it, you make a plug that's slightly larger than the hole, you cool the plug, heat the cylinder, drop the plug in two. When the two things thermally equilibrate, you've got the plug inside expands. right? What that does is set up a very easily sort of like measurable stress distribution where the plug's in compression and the outside you've got some tension dropping off. And so we produced a series of these and then passed them around to different labs, right? And this is just a small subset of the measurements. The reason I'm drawing your attention to this is that it's very, there were 6 labs that made these measurements, right? Everyone basically got the same thing, right? It's fairly intuitive what you're going to do. But if you actually look at the difference here between, I don't know which lab, say this lab and that lab, right? There's a swing here in the compressive strain in this case, but you can say stress, that you actually saw that was probably, 50%, right? It's a swing from one side to the other. If you're writing an intuitive paper asking the question, what's the stress profile in the system, right? It doesn't matter, right? I can give this talk perfectly happily. If you're going to draw a conclusion, that relates to whether or not this is safe in some application, you better be sure that you understand why these labs are measuring something that's 50% different on 2 different samples, right? It's not far removed from, the discussions about calibration and standardization that we all have as good scientists. It's just got a bigger impact, right? Because, people won't take you credibly, right, if you can't say that a measurement at Oak Ridge is going to be the same as a measurement at Los Alamos, is going to be the same as a measurement at some other reactor. So I'm just drawing your attention to the import of that. I think, this is just the time scale, so, the first ideas were proposed in the 70s. The first dedicated instruments are sort of like we're appearing here in the 90s and late 90s, right? And so now, you've got instruments like Vulcan, right? Instrument like the new instrument that's going to come on at the ESS in half a dozen years. So I think by now you're probably at least cosmetically familiar with neutron X-ray diffraction for strain measurements. But let me just revisit the import a little. A lot of the early work focused on macro stress measurements, type 1 stresses. It's easiest and most tangibly visible here. You generally don't think of rail track as having a lifetime on it. Most rail is certified for a billion tons. I'm not exactly sure what the metric is, right? It just goes backwards and forwards. But the lifetime of any particular piece of rail relates to, whether it's on a curve, how much friction, whether it's lubricated, grinding, temperatures, how well it's supported underneath. And all of those things matter, right, as it relates to, for example, fatigue cracks propagating through the rail. But another big part of that then affects whether or not something's going to fail is the residual stresses that you get in the rail. Right? So when you fabricate rail, you get residual stresses of the sorts that you now are qualitatively familiar with. This was a piece of rail that in the 80s was the sort of source of a problem in Texas. It had been run, track had run it over it, trains had run over it for many years. And then they found a small problem with it, and they basically came in with the repair problem, right? And so in the repair, instead of the top layer being flat, there was a small step in it, right? Remember, this is rail that had been in service for many years. They did the repair, there was a step, right? When the next train came along, a crack propagated, right, from the step, but instead of being limited in the surface, it made it down into what was called the web, right? And what this shows, right, is a reconstruction of the rail after the fact, right? Remember, this is rail that has been, in service for many years, right? What happened was because of the repair that had this height mismatch, the crack that would typically have been impeded at the surface made it down into the web. The web had residual stress in it, right? And it was, as long as the crack didn't make it there, it wasn't a big deal. But once it made it there, it just peeled apart, right? So, that's why, type 1 macro stresses, are a really big issue, and it's why people spend a lot of time understanding and modeling them. So first approximation, engineers, see cracks like this. And engineers are very good at running continuum mechanics calculations with finite element systems, right, for actually predicting, continuum material performance and actually sort of like saying safe or not safe based on the sorts of safety factors that I alluded to in that silly little comic at the outset, right? You put a safety factor of 2 on it and then you can be reasonably confident it's going to be safe. Physicists down here, sort of like at the atomistic level, are reasonably deterministically confident that they understand, I'm going to say, failure or how deformation takes place at the atomistic level. The big challenge for material science and engineering to get the most out of measurements is in this middle region here, right? It's the region around the microstructure, the region where you have defects and interfaces, and by now you've almost certainly heard the expression mesoscale, right? It's where a lot of focus comes for actually making the jump from macroscale predictions of performance to deterministically understanding the sorts of things that take place at grain boundaries, the sorts of things that take place in sort of phase separation, and then linking it down to deterministic models, sort of like at the atomistic scale. And I'm going to come back to this right at the end of my talk. So by now, you're familiar with polycrystalline diffraction. Sorry, polycrystalline diffraction. By now, you're well aware that when you see these peaks, what you're doing is basically selecting out a set of grains in particular orientation with respect to a particular load in order to make the measurements. In a cubic millimeter of material, right, if you've got a grain size, right, of a micron or so, you've got 1 billion grains. Right? And so you're looking at a subset of those. When you do diffraction measurements, and I don't doubt that you're here, you can pull out, you've done this before, you can pull out a peak position, you can pull out a peak width, you can pull out a peak intensity. From the peak position, right, if you put a load on it, right, you measure changes in this position, you can relate it in principle to the macrostress, type 1, type 2, possibly even the type 3 strains in the material. It's worth noting, though, that the peak position is also sensitive to chemical composition, the D0 problem that you've been exposed to, and temperature. The key issue here is that your engineer is asking you about these stresses because he or she knows how to relate that to a lifetime prediction. If your measurements don't account for this or for that, you can get a result that is basically meaningless, right? Although we don't spend a lot of time doing it, you can also pull information out of peak width. It's a subject of a talk, a rather more sophisticated talk. We spend a fair amount of time at Los Alamos relating peak widths to dislocation densities. You can do that on any high resolution instrument, such as the ones that you have here. You can relate this sort of dislocation density to radiation damage. It's another engineering related problem. And of course, in the diffraction pattern, you can also pull information out from the peak intensity, right? In a composite, different phase fractions, you've got texture is a huge deal in disorder. I think as we go along, somewhere along the line, you might naturally say, well, what are the problems for which a reactor is better suited, and what are the problems for which a spallation source is better suited? Considerations about position and width and intensity and how much information you get out in an individual measurement all relate to that. There are classes of problems which you do better at a reactor and classes of problems that you do better at a spallation source. Okay, by now you're familiar, I think, this relationship between stress, strain, interplanar spacings. Here's my one equation, Bragg's law, let me not belabor it. Strain, D0, I know you talked about it, right? And then, you know, when you actually make the step to convert to stresses, there's something else that's important, and that's the stiffness of the material. So where can you go wrong with doing stress measurements? I shouldn't say go wrong. What are the things you need to consider? You know, when you use diffraction for doing a stress measurement residual in the material, you're basically just looking at these sort of springs, these spring constants pulling atoms apart. D0 is affected by chemistry. The other thing that you may not have been paying much attention to yet is the fact that the stiffness is HKL and texture dependent, so that the stiffness between these grains for different lattice reflections is different in one direction than it is in another direction, right? And you have to understand that. And you have to understand how that stiffness varies both intrinsically in the crystal. So if you want to go to the security detector, knock yourself out. Let's see. So particularly in materials which have been heavily processed, the presence of texture can significantly affect the macroscopic properties in different directions. All right. There are other complications. The scattering geometry. One of the big issues with stress measurements, if you're doing spatially resolved, is if the sampling volume comes out close to the surface, and so instead of being fully immersed, it's only half in and half out, right? What that does is introduce sort of like artifact peak shifts that can also affect the results, right? You know, beam optics, peak shapes. If you're going to make the step from strain to a true stress tensor, you don't get to do that with just 3 measurements. You have to make a minimum of 6 and potentially more, right? So now, you know, very few people do that. You know, and then there's this question of interfacility comparison. All of these things are complications to actually, you know, to do good science. So now let me spin over some instrumentation, and then I'll get to the 2 examples that I want to talk about, probably more interesting to you. First approximation, for neutron measurements, there are sort of 2 modes, spatially resolved. Spallation neutron source, you do it with radial collimators. At a reactor source, you typically use apertures pushed up close to the sample. Both facilities, you know, frequently support measurements with load frames. There's lots of science that you can do by putting a known load on there. At a high energy synchrotron X-ray light source, the typical mode is to take, you know, X-rays, if you're doing engineering where you have to get through appreciable thicknesses of some polycrystalline metal that is engineering relevant, you're typically operating at 50 to 100 keV. That means that because the wavelength is short, your diffraction is now, unlike in the reactor source, where, the neutron source, where your wavelengths basically allow diffraction at 90 degrees, which helps you define a nice, easy, sort of well-defined sampling volume, little sort of cuboid, sort of like roughly there. You know, and you know, even go into sort of like backscattering geometry. For most engineering measurements at the light source, because you've got short wavelengths, you know, you're typically looking in a forward scattering direction, and so you're putting all of your diffraction rings on a detector that's downstream, and you don't have that same ability to define a sampling volume that you do at a neutron source. Doesn't mean you can't do measurements, but you can do very good measurements, but you can't define the 3D space. The emphasis on engineering scale components means that instruments typically have to accommodate, you know, big objects. One thing engineers do not like doing, for the most part, is inferring something from a sample that's been cut out of the part that you care about, right? So you can see a wing spar, you can see a jet engine, right? You know, these are engineering style objects that have been brought to a facility, right? And so the facility has to accommodate that. The corollary to that is that there's a series of compromises in designing an engineering instrument that make it different from an instrument that's optimized for doing, just diffraction, right? For a long time, diffraction measurements at sources, such as, SNS, such as Los Alamos, said, okay, my sample is going to be a powder, or it's going to be something a few cubic millimeters, right? And so I'm going to build my instrument to have the best possible resolution, the lowest possible background, and the best ability to define, put an environment on a sample and collect the diffraction data that I want. For engineering instruments, because you have to handle, the wing spar from an airplane, right, or a jet engine, the questions that you're trying to achieve in the instrument are, you need to be able to align it to, micron scale spatial resolution. You need to be able to accommodate objects that may weigh, 1,000 kilograms or more, move them around, and then have apertures that come in as close as possible, and put radial collimators in there. And so you end up with instruments that look very different from classical powder diffractometers. I imagine you've looked at Vulcan. Smarts looks very similar. And of course, in the future, if you want to see where people are going with this, this is a concept for the Beer engineering spectrometer at the ESS, due online in half a dozen years or so. These two slides just sort of show you, instruments that existed. I pulled them from something else. And so let me turn now to two examples that illustrate different aspects of sort of what you can do with neutrons and X-rays. This is work by Chev Nguyen, Adrian Brugger, and some guys at Los Alamos, where they were actually used the neutrons to study 7-wire strands in bridge cables. Okay, so what's the problem? There are 600,000 bridges in the US. Their average age is about 40 years. From a civil engineering point of view, about 1 in 9 is rated as deficient. Right, so imagine how much traffic is going over these bridges. The worry is that it does this. To actually correct the deficiencies, and not every deficiency says that the bridge is going to collapse next year, but many deficiencies says there's something that you need to pay attention to. It'll be $20 billion. I'll leave it to you to decide whether or not we're going to spend that on US infrastructure. One subset of the problem relates to suspension bridges, right? Elegant, all the load is carried by these cables that are under tension, right? They've been around since the Golden Gate Bridge and before. The bridge cables themselves, that's carrying all of the load, basically are comprised of these sort of like, mesh of very tiny little cables that have got, diameters, that are small compared, this is a meter or two, this is a meter, right? And so you can see these lots of individual cables running down the middle. And so when you look at the Golden Gate Bridge or the Brooklyn Bridge, this is what's inside the cables that are holding the roadway. It's well known that some of these individual strands break from time to time. It's not a big deal, right? The question for an engineer is that, and the approach to actually looking at this is that, from time to time they come in and they, pop open these strands, and then they take a look and they look to see how many they can see that are broken, and then they relate that statistics of breakage to some model that says, we're closer or further away from a point at which we have to take this bridge out of service. One of the questions that relates to the strands is, if you've got a bundle of strands, right, and the one in the middle breaks, does that mean that it no longer contributes to the load-bearing capacity of the whole bridge, right? Or in practice, what actually happens is that if the strand in the middle breaks, right, because it's clamped, right, at different locations, even though there's a break right here in the middle, right, some distance away from that break, the strand is still contributing to the load, right? How far that distance is fed into the calculations and relates to the models as to whether or not you should take the bridge out of service or not. Right? Pretty big deal. right? And so one of the a classic neutron problem is that suppose I've got a clamped series of bundle of cables, I've got a cable in the middle of this is broken, right? And I'm wondering, well, how far along the central cable or the surrounding cables, can I see that there's a break in here? What you can do is define a sampling volume. You can put a load on this set, set up a situation which is probably fairly familiar by now, slit, sampling volume, radial collimators. Now you can ask what's the strain that takes place or exists in multiple places. You put a crack in the middle, you load it up. What do you see? If there's no break, right, all of the wires, all of these 6 or 7 strands, you look at them individually, sort of show much the same response. Here's the applied load. Here's the measured elastic strain, right? Everything's hunky-dory. When you get a break in just one of them, right, what you see is that the whole thing doesn't break, right, at that point. But what happens is, this is the applied load. On the cable that broke, as you increase the load, the strain is now dropping, right? It doesn't go to 0. It didn't go down here. It's just unloading a little, while the surrounding cables take up more strain. So this is applied load. This is the measured elastic strain, right? And so what you can see in this scenario is that the cable that broke, or the strand that broke, is unloading. The strands that didn't break are taking up more load. And now, in this graph, right, what you find is that when you unload, right, so let's say that you got to an applied stress of somewhere between 350 and 400 MPa, you can see all these coming back down to 0, right, as you take the load off. But here's the interesting thing. When you load it up again now on the next cycle, this strand that was broken, right, it doesn't follow up the original line, but it does take load here, right? And these other strands, right, come up a different line here, right? So, and this reflects the fact that in this particular location, right, you could make measurements sort of like in the broken cable and surrounding cables. Now, I'm only showing you a tiny subset of this overall study, right? From, this is, I grabbed these slides from Don Brown before, but this work has moved on considerably since then. But it does show, the neutrons can make measurements in here, and it can make measurements in here, and they can make measurements along the strands. That's a uniquely neutron problem. So now let me turn to a uniquely X-ray problem, or unique X-ray problem. Additive manufacturing, 3D printing, much in vogue right now. The idea that you can net shape form a component by taking a powder, right, taking a laser, driving the laser over it, and you can build up the component that you want, right, basically from powder, right? Much excitement about that. No shortage of excitement in places like Los Alamos, right? The reason for it is that there's a lot of historical processing capability that doesn't exist anymore in the complex, and the idea that you could build up a part, from a powder and just sort of like laser, and then an hour later, 2 hours later, you've got an object is very exciting. Built-in functionality, particularly appropriate, for somewhere like Los Alamos where you want to make small lots of complex geometries, right? There's a cost point there, right, for actually doing it. It has relatively minimal footprint. There is a gigantic challenge that is by no means Los Alamos specific, and that's how do you certify additively manufactured material, right? How do you certify, it's what's called product rather than process-based qualification, right? How do you understand the process structure property performance? The challenges in doing this, derive from the fact that, quench rates, in additive can be as much as 1 million degrees a second. Phase changes, temperature builds, phase topography, starting powders, right? You've got a whole series of phenomena here, that change from microseconds to hours and from microns to the scale of the component. And so, because this is a new arena, the sorts of tools that you've been learning about, that study surfaces, that study bulk, that study phase, can be brought to many aspects of this. And I'm going to focus just on one of them, is that, for these phase changes, right, that takes place, you've got a lot of phenomena that are taking place at the sub-second time scale, right? It's rare, not impossible, but rare that for engineering measurements that neutron sources can touch sub-second, right? They work much better for scenarios where you're actually looking at these, heat treatments, right? You're looking at changes that take place over the duration of the build, which is sort of like minutes and hours. But we said we want to understand some of the phase transformation performance that takes place during an additive manufacturing process. And this is not quite additive manufacturing in the sense that I described it as a weld and powder, but what John Brown, John Carpenter, and Jason Cooley did in collaboration with the folks at APS and 1ID was basically build this wheel, right, with what's called a cold metal transverse weld. Cold metal transfer weld is basically a variation on metal arc welding, right, in which you have a wire feed that comes out on a wheel. It measures the current and it pulls it back and brings it back in and out. And we wanted to see, we actually also put a laser on this, but we didn't use it for the data that I'm going to show you. We wanted to see how much you could actually infer about strain and phase change and diffraction as the welding process was going on. So, the weld itself, whoops, I'll do this, it's just a pretty picture. When it actually starts going, right, so you can see that this was in the hutch as the weld was being deposited, right? So what we're asking, using the X-rays, is actually what's going on in the middle of this weld pool as the weld is going around, right? And I can be pretty confident this is one of the first times that anyone's ever actually had insight on something like this. The measurements that we made, and sorry, this is the resolution is a bit poor here, and a last minute problem. There were two sets of measurements that we made, right? And actually there's a couple of things to think about. We made the weld with the wheel rotating, right? And the reason that we did that was that we wanted a fixed geometry, right, whereby we could actually move both an imaging viewer, right, and a diffraction spot relative to the weld pool, right? It's not fast enough to actually get everything as it goes by, right? So we had the wheel going, we started the welder, right, and then we made measurements sort of like, with diffraction spot and then with an imaging field of view, and although it doesn't show it in the movie, I take this imaging field of view and I drag it down here, we move it backwards and forwards right now. This right now is proof of principle that you can do it. The diffraction data, which I'll show you second, you can actually get more data out of it. Remember that the wheel is rotating by about 1 millimeter per second. Diffraction spot size, diffraction count time is about 1/10 of a second. Diffraction spot size was, I think it was 0.1 or 0.2 millimeters, and then it was about 1/10 of a second for the imaging as well. So this movie is not very compelling until you sort of start thinking what you're looking at. Remember that when I showed you that the bright movie with the sort of like the sharp flashing going on, right? What's happening there is that the wire is protruding out. You're forming a molten weld pool. The wheel is pulling it out. What you're looking at here is this was just proof of principle. We could do it, and you can see this thing prodding out here, and then occasionally what they're doing is dragging around the imager relative to the weld itself. where I'm looking at right now is just on the top of the wheel, and this is the leading edge of the weld with a 1/10 of a second resolution, right? It's not quite good enough to give us what we want yet, right? And so now if you watch it just at the end, right, you'll see they're moving the field of view. This white line, right, was the wheel itself coming up into the field of view. It stopped, we turned it off, right? And if you notice closely, just at the end there, you know, when you start it, it contracts, right? So it's still moving, you watch it, you can see it shrinking, and then you end up with these sort of light features, right? You know, right now, I'm not ready to say whether these features are at the surface, but some of these features are porosity in the leading edge of the weld, right? It's easy enough to see them after it's frozen. The challenge for the technique is to actually be able to see whether or not you could draw some conclusions about this porosity during the weld process. If you could, and you could see it and you can extract the information, you could optimize the welding parameters. Okay, so that's pretty pictures with a lot of potential, right? Particularly if you can get better resolution and better temporal resolution. Let's turn to diffraction, where it's a little bit easier to see something quantifiable out of here immediately. What we did, here's the wheel. You know, when we drop the weld down, right, the first thing is, so initially the diffraction spot is sitting here. The weld will come back here, and I'll start the movie in a second, you'll see. And now we're going to drag the diffraction spot in front of and then behind the weld, right? We did all of this manually, so it's not quite as elegant, you know, as you might hope to see, but let me run the movie and you'll see. So we turn it on, the weld starts, the diffraction spot is here, right? You can see a series of rings, if you remember from your diffraction at APS, right? We dragged the spot in front of, back through the weld pool, and then back, and now it's drifting back here. I'll run it again, 0.2 millimeter second, 1 second integration time. Remember, you're getting diffraction data out of it. So let me just, so remember, you know, the weld pool is sitting here. This is diffraction. The fact that you've got individual rings means that you've got some polycrystalline diffraction going on. The fact you've got this big, broad splodge is telling you something about the weld pool itself. I'll show it to you interrupted in a second. Ignore the horizontal lines. That's noise coming from the welder. So if I just let it run through, and I'll interrupt it, show you the interrupted slices. We're dragging through, back here. Now, as you come back here, you know, this is a second behind the weld front. This is a few seconds behind the weld front, right? The wheel is turning at a millimeter a second or so. So this is 5 or 6 seconds behind the weld, right? And you can see that there's no longer molten metal here, and you've got, you know, a series of diffraction information on your transmitted sort of diffraction detector. If I integrate those rings to give you diffraction patterns that you're more familiar with, again, ignore the spikes. What you will see, and again, this is just the diffraction images of the integrated rings as you track it backwards and forwards. You know, you can see the diffraction pattern changing. A couple of things to note. I'll run it again, right? Look for the bump here, which is molten. You can ignore that jump right at the end. You just run it again. Look, when I run it again, look for the bump here. And something else to bear in mind is that in this material, there's an austenitic phase and a ferritic phase. This is the austenitic phase, this is the ferritic phase, right? I want you to look at this dotted line. See, I'm running out of time, so let me go quickly. Right, so I started it halfway through, but you can see the peak shifting to the left. That's as the material cools at the end. So now, if I just go through these one at a time, in the molten weld pool, no diffraction patterns, this big, broad hump that you come from the liquid. Leading edge of the whirlpool, look at the relative intensity of the ferritic peak and the austenitic peak, and that's probably because what you're actually seeing is the wire feed. Trailing edge of the whirlpool, right? A couple of things to note. You can still see the molten metal. These rings are complete here right now. You've got complete rings, elegant, right? So that means you've probably got small grains and very little texture. About 5 millimeters behind the whirlpool, right? You know, the material is now uniformly solid, but it's cooling down, right? If you look, the rings are pretty continuous here, right? You know, there's lots of spots in them, right? But they've got big breaks in them. That's sort of consistent with the material being textured. And then when you go all the way back out here to 10 millimeters behind the weld, right, you can see, right, that the rings have become very spotty, right? Still got some gaps. It's qualitatively different from this, right? And from that, you can infer that you probably got large and annealed grains, right? You've done all of this, you know, in a few seconds after the welding process, right? And then you can relate this to sort of like offline characterization after the fact. But, you know, hopefully you can see the power of doing this. So, by way of conclusion, I hope I've showed you, you know, that diffraction is a measurement of elastic strain, phase in grains and crystalline materials. Although I haven't belabored it, the time, length, and geometry of the experiment determines whether or not neutrons or X-rays are the better way to go. Although I haven't talked about it, in practice, neutron X-ray measurements are often used as validation tools for other destructive measurements, right? Because there's only one SNS and there's only one APS, you can't bring it to bear on every problem that you have. But if you've got some other tool that you're using, strain gauges or drilling or some other approach, but using the opportunities implicit in X-ray, neutrons and X-rays really helps. For engineering measurements, because an engineering user is typically not an expert, has no interest in being an expert, there's a real opportunity for people at facilities to be able to operate in that middle ground between doing fundamental science that is the return on investment that facilities like this, and while at the same time making the measurements that impact the real world, whether it's optimizing a welding process, finding a new material, or seeing whether a bridge cable is safe. Standards and scientific support are what makes instruments successful. And by way of conclusion, where do I see the future going? This probably reflects a Los Alamos-centric view of the world, but the opportunities implicit in exascale computing and the massive computing power that's coming along means that for the first time you've really got the opportunity to actually draw insights on structure properties at the mesoscale and relate it both down to atomistic and up to macroscale. And so I'm pretty confident that the future of our use, and this is now Los Alamos, of facilities like the SNS, like APS, and to be honest, of LCLS, right, the free electron laser, will relate to, multi-probe in situ transient measurements of the sorts of things that I've been talking about, and then relating them to exascale computing. So, with that, thanks for your attention. Please. Yeah.
Do we ever have problems with inelastic strain in these types of materials? And if so, how do we measure them?
So, oh yes, the question was, do we have problems with inelastic strain? Whenever you're measuring the separation of the lattice planes and we're inferring residual stresses from that, I'm talking about elastic strain. When you say inelastic strain, if you put dislocations into material, right? So that the material is now, this big instead of that large. You can have a situation where there are no macro residual stresses in there. If you just take a uniaxial load and you put 1% strain on it, right? And now if I look at this location and that location, the despacing you get will be exactly the same. What will be different, because you've got dislocations, is that the peaks are broadened, right? I alluded to that a little bit, right? So when you say inelastic strain, I tend to think about, the broadening that you get from dislocations in material, and that's accessible, right? Whether it's from radiation damage or plastic, right? That's a variation of the sort of data you can get out of diffraction data. Now, I'm not sure if I answered your question or not. You did? Okay, good. Thank you.